Hello everyone and welcome to today's preview briefing about the upcoming Orion flight test. During the test, Orion will travel on a two-orbit, 4.5-hour flight designed to stress many of the spacecraft's critical systems before Orion begins carrying humans on future missions. Here to share more about Orion and its upcoming flight test are Bill Hill, Deputy Associate Administrator for Exploration Systems Development, Mark Geyer, Orion Program Manager, Brian Austin, Lockheed Martin Mission Director. Joining us from NASA's Johnson Space Center in Houston, Mike Serafin, Orion Flight Director. Back here at Kennedy Space Center, Jeremy Graber, Recovery Director, and Ron Fortson, United Launch Alliance Director of Mission Management. Those of you watching from afar today can ask questions using the hashtag AskNASA on social media. We'll start here with some opening remarks, and then we'll take questions. With that, let's start with you, Bill.
Good morning. 4 weeks from today, at about this time, we'll be about a half an hour from splashdown, hopefully, if we get off on time. Kind of wanted to start off by talking about last week's events with the orbital Antares launch failure and the Virgin Galactic Spaceship Two incident. We just want to reiterate that space operations is hard, and they proved that last week. It was a tough week. It's a tough business we're in. Right now, between what we see for EFT-1, there really wasn't any related systems or things that we might want to go look at for failure investigation, but we believe that both will come back. They've got good teams. In the space business, we're one big family, and when somebody has a failure, we all feel it and we all rally behind them to make a return to flight, and we expect them to do that. EFT-1 is absolutely the biggest thing that this agency is going to do this year, and I may be partial because it's in my area, but I think it is absolutely the biggest thing we're going to do. We took a different approach with EFT-1. We're basically buying services from Lockheed Martin, and we've asked them to go procure the launch vehicle, which they did, and work through all that. They are responsible for the mission. It is truly a commercial endeavor. The launch and entry are both FAA licensed, with ULA having the license for the launch and Lockheed Martin for the entry. Our mission operations folks, and you'll hear from Mike Serafin, and our ground systems folks, Jeremy is working, are basically subcontractors to Lockheed Martin in both doing the mission ops and the flight ops, as well as the actual recovery. This is really our first step in our journey to Mars. We look forward to exploring, and in exploring, we look at it as basically a three-pronged approach with the International Space Station, commercial crew, and our exploration systems that we're developing as a triad of human spaceflight. The space station is a great platform for proving out technologies, and we're doing that, getting ready for Orion in the long run. And obviously, we need commercial crew. So basically, we need all three to be successful, and we're approaching it that way. And that's basically all I have. I'll turn it over to Mark.
Okay, thanks, Bill. I'm going to talk about a couple of things. First, I'll talk about what is EFT-1, what's the purpose, and then I'll talk a little bit about how EFT-1 relates to the vehicles we're going to fly people on and how similar they are. So let's go to the first chart. There's a picture of the crew module in black. Those are the tiles that you see there. It's mated to the service module in this picture. EFT-1 is primarily a crew module test, and I'll talk about why that is, because that is the core of Orion, and we're testing key systems there. If you go to the next chart, you'll kind of we'll get a panning, or there's a picture of the whole Orion on top of the adapter that we got from the rocket guys from SLS. The service module is below that in the fairings. The capsule is on top of that, and now the capsule is encased by the launch abort system, which you see there on the top. Whole stack is about 72 feet. It's a big piece of hardware. We'll actually roll out to the pad and be lifted onto the rocket on the 11th of November. So that'll be a big day for us. And basically, Orion is done. We're completed, buttoned up, ready to go. So let's go to the next page. What is EFT1? Well, there's a picture of Orion when we are flying people, the full complement of systems. And then on the next page, let's talk about EFT1. EFT1 was basically, so next page. There you go. Okay, that might be a little hard to read. What I wanted seemed better when I actually was looking at it on my screen. EFT1 is basically a compilation of what I would say the riskiest events that we're going to see when we fly people, and I'll talk about each of those. So this test flight is a great opportunity for us to fly those and actually see them in operation. Some of these events are very difficult or even impossible to test on the ground, so it's important to fly them. So EFT1 gives us a chance to put all those together in a test flight. So if we go ahead, let's try, we'll go to the next page, and there are 17 separation events on the left, upper left. These are basically things like we jettison the service module fairings. The service module fairings are there basically as a weight reduction effort. They help carry the load on the way up, but we dump them so we don't have to push them to the moon. The launch abort system will also be jettisoned on this test. It's another critical event. We'll separate the crew module from the service module. A lot of things that have to work right the first time. And so they're key events, and we're going to test them on this flight. Some of those we've done tests on the ground again, but you really need to test them in the flight environment. So that's why this is such a big test. So go back to the chart again on the right, the heat shield. Obviously, we've talked a lot about that. We're going to go 3,600 miles into space. We're going to enter at about 20,000 miles an hour. It's about 84% of a lunar entry, so we get very close to what it's going to be like coming back from the moon. The heat shield's going to see about 4,000 degrees. It's about 1.6 inches thick. Will burn off. We project about 20% of that will burn off. That's part of the nominal plan. Of course, the big part of this test is we'll get it back, we'll look at it and see how did it perform. There's a lot of uncertainty relative to the aerodynamics and the flow and those kind of things on this particular heat shield, which is the biggest heat shield that's ever been made. Next page, or go to one more slide. So radiation, obviously, we're going to be flying very close and through parts of the Van Allen belts. Since we are 15 times higher than the space station would not deal with that radiation level, but we will, and any vehicle that goes on to the moon is going to have to deal with that. Why does that matter? That's a big issue for the computers. Now with these processors that now are so small, they're great for speed and for size, but they are more susceptible to radiation. So we expect, we have a design that if we get some, let's say, upsets, the computers might reset. This is something that we plan for. We have redundancy, and we have ways for us to bring those back up and support the mission. We also have timed some of our key events to be outside this region, so again, to protect ourselves. But that's one thing that we have to design for, and we have to actually see how it behaves. And then the last piece is really the parachutes. You know, we're going to go from about 300 miles an hour to 20 miles an hour. The crew obviously is not going to land at 300 miles an hour. We need to slow it down. So even after the heat shield deploys, the parachutes have to help slow us down. So we have 2 drogue chutes and 3 mains. Those are the main part of slowing the vehicle down. Again, we've done drop tests out in Yuma. You get kind of close with certain environments, but we haven't never done a real full entry from space, and this will be our first chance to make sure everything deploys and operates as it should. So that's a big part of it. The next thing I wanted to show you was, let's go to some slides to say, this is a picture of Orion on EFT1, and how similar is it to what you're going to see when we actually fly people. So let's click through that. First, let's start with the crew module itself. So we are flying a flight primary structure. So you could fly people in this primary structure. You could fly people with this heat shield, with the forward bay cover, and with these parachutes. What we found as we built EFT1 and as we're flying it, we will find things that we decide to update. And for example, we found that they are part of the primary structure. After we built it, we found a way to actually make it lighter. And so while it is a flyable structure for people, we're actually going to lighten that structure, and the structure for the very next build, which is EM1, is already in manufacture in Southern California, and it's 25% lighter. So these are things you learn when you actually build a system, and you actually build a flight system that you're going to send into space. So let's go to the next page. The launch abort system, of course, on this flight, there's nobody on this element, so we don't have an abort motor, because we don't need to abort. There aren't people on board. But we do need the jettison motor, because the jettison motor actually pulls this cap off the top of the crew module. That has to happen successfully every flight, and so we'll test that on this flight. It's a flight structure, it's a real jettison motor. Next page. The service module is primarily structure, and we're testing how it behaves, the loads and environments that it will see. The back part of that service module now is actually going to be provided by ESA, so that'll actually be updated before EM1. But the front part, that ring, is very similar to what we'll fly when we fly people. And then the next chart is the adapter and the fairings. Those are flight-like, so we'll tweak those a little bit. And I expect we're going to learn a lot on this flight, too, on how they behave in the environment. So I just wanted to give you a sense for this is real hardware that we intend to fly people on, and we are flying it now in space, and we will update as needed for things we learn. So that's primarily all I had, so I'll pass it on to Brian.
Thanks, Mark. As Rachel mentioned, I'll be leading our Orion mission management team for Lockheed Martin. I just want to say how proud I am and how proud Lockheed Martin is to be partnered with Mark and the NASA team in making this mission a reality. EFT-1 is a risk reduction flight. It's in a series of risk reduction flights in that campaign that will culminate in putting crew on the first flight in EM2. Some of the mission objectives, just a more detailed focus on those. Of course, Mark went across the gamut of what's crucial to the success of this vehicle and the success of the flight. We're going to focus on the critical separation events throughout ascent and deorbit from all the separations that we have and through the spacecraft separation. Of course, again, critical to that is the thermal protection system and demonstrating its performance in a high energy entry return, similar to what we'd see coming back from deep space and beyond the moon. And then the landing and recovery systems and the operations of the recovery itself are critical to reducing the risks and getting us in a good posture to put crew on this vehicle. Through that, we're building a very safe and reliable spacecraft and looking forward to taking it beyond Earth orbit, beyond the moon, exploring deep space, as Bill mentioned, and then soon taking us to Mars. This flight, as a test flight, is extremely instrumented. We'll have development flight instrumentation throughout the vehicle, really focusing on the stresses and the temperatures that the vehicle is going to experience. We'll also have our operational instrumentation for the teams on the ground to monitor and respond to. And then, of course, we'll have imaging that we'll have an airborne imaging near the recovery zone, higher altitude aircraft, helicopters looking at the spacecraft and assisting in the recovery of the chutes and the other elements around the spacecraft. An event like this is significant, and through this significant event, it requires good teamwork. And again, I mentioned our partnership with NASA. Somewhat unique on this flight is NASA is asking for a service and providing the data back. But across the entire design of the Orion, it's been very evident how successful that teamwork's been. From the design, through the production, through the risk assessments, the contingency planning, and now into the mission execution, that teamwork has really been vital and is proving very productive and making us a very efficient and effective team. It's going to be evident as well in the mission itself. I'll talk a little bit about the mission execution. Throughout the operations teams, the engineering teams, and our mission management teams, we'll have both Lockheed Martin and NASA personnel in each of those blended teams working together. In Florida, for the launch and the operations and checkout building, we'll have our engineering support team, and the launch operations team will be over there. We'll begin the activation of the spacecraft about 6 hours before launch. After we launch, that handover of that control and monitoring of the spacecraft goes to the flight operations team. Mike Serafin's the flight director in Houston in the MCC. And then, of course, the recovery team and Jeremy will be on the ship waiting to receive the spacecraft and bring it into the ship. Our mission management team, Mark, myself, and our other team of NASA and Lockheed folks will be on the Air Force side here at KSC in the Hangar AE in the Mission Director Center. We'll be following the activities of the countdown, following those activities, the launch vehicle, as well as during the flight. There to execute any discussions and potential waivers that we might have to come across for pre-launch, for launch commit criteria, as well as anything that might come up in flight. We've got flight rules, obviously, that describe how we're going to respond to any contingencies in the mission. But if we get outside of those boundaries, then our team will be available to evaluate the risk and make the decisions we need to continue to get this vehicle back to the ground. We're getting close. We're about inside of a month to launch. The final preparations are going on. Next week's going to be pretty exciting. We're rolling out of the LASF facility, rolling over to the ULA and getting stacked up on top of a rather large Delta IV Heavy rocket. In addition, next week we'll have our final mission rehearsal with the Orion team, a full mission rehearsal. That'll go from launch minus 6 hours, basically activation, all the way through the launch and the flight and into landing and the early part of the recovery. So a very long day, but very representative of what the team will experience December 4th. Just a little bit about the day of launch. Again, December 4th, our launch window is 2.5 hours, 2 hours 40 minutes to be more closely to the right time. We'll be launching early in the morning, 7:05, driven primarily for lighting on ascent, again, to get the imaging that we want to see so we can truly evaluate those ascent separation events, and then provide the most amount of lighting and day-lit opportunity for the recovery team to effect a recovery from the spacecraft. Just add to what Bill mentioned, space flight is tough, and the environment of the leaving Earth and returning Earth is probably some of the toughest environment, most dynamic and time-critical environments that we see flying humans in space. This flight test and this campaign of flight tests are crucial to really understanding those environments of deep space as well, and making this vehicle the safest we possibly can, because we want to take the crew out and give them a home, give them a platform that'll handle them from a long time, their new home away from home, if you will. With that, I'll turn over to Jeremy. He can give you some more details on the recovery.
I think we'll actually go to Mike Serafin at JSC.
Sorry, Mike.
Well, good morning. I'm Mike Serafin. I'm the lead flight director responsible for the flight operations for Orion's first flight test. I'll be supporting with a team of blended operators. They're all legacy shuttle operators that I've worked missions with before out of the Mission Control Center here in Houston. I wanted to provide a brief bit of insight to some of the mission preparations and the environment that we'll be supporting flight operations from. So if we could pull up the first slide. This shows what the blue flight control room looks like now. It was previously used by the International Space Station program from 1998 when the International Space Station first started flying through 2006 when the International Space Station team outgrew this room because the space station continued to grow in terms of systems, capability, and then also crew size. The operators here have all built and trained and tested all of the applications and software you see there. The room was completely renovated in the 2012-2013 timeframe, everything from new paint and carpet to consoles. The hardware and software is new, and it's all been tested and checked out. We've trained on it, and with our United Launch Alliance counterparts, the launch operations team led by Lockheed Martin out of the Cape, and then the recovery operations team on the recovery ship. We've exercised all those interfaces, and we're going to do as Brian said, our final mission dress rehearsal next week. So we are getting very close to flying. We're about 4 weeks out, and the team is ready, and we're ready to go fly Orion on this first flight test. All of the operators in the room, they're pretty standard to what you've seen for previous spacecraft. We have experts on electrical systems, common track systems, guidance and nav systems, as well as folks that monitor the navigation state and the trajectory on board the spacecraft, and then we'll also be assessing the weather at the splashdown zone. So we've got a good blended team of operators, and they're all experienced, and we're gonna check out Orion and monitor its health and status leading up to splashdown, and then if there are any things that the recovery team needs to deal with, we'll have insight to that via our telemeter data into Mission Control here in Houston. We'll relay that out to Jeremy Graber and the recovery team so that they understand the situation that they'll be getting themselves in. Otherwise, we'll just relay the splashdown location, and they'll know when and where to look to gather imagery at the splashdown time, as well as where to recover the Orion capsule. I do want to talk briefly about the mission trajectory and give you some insight as to how the mission is going to look from an Earth orbit point of view. Again, we're going to be launching out of Florida, Launch Complex 37 on the Air Force side. Perform 2 orbits. The second orbit will be a high Earth orbit, getting up to 3,600 statute miles above the Earth, or over 3,000 nautical miles. And on the entry side, we'll set up a high-speed reentry. and that'll test out the heat shield splashing down off the coast of Mexico near the tip of the Baja Peninsula. In terms of where we're going to fly over the Earth, our ground track, again, is a due east trajectory out of Florida. It'll take us out over the Atlantic Ocean, the southern tip of Africa, again over the Pacific Ocean, and then when we cross over Texas and on our second lap around the Earth, we'll do our orbit adjust burn, our second stage burn 2, setting up that high Earth orbit and entry interface leading to splashdown off the coast of Mexico. The upper stage and the service module will deorbit north of Hawaii. It'll be an uncontrolled reentry for the upper stage and the service module. In terms of the altitude profile, the altitude on the first orbit is going to look similar to what we've seen for previous space shuttle missions and is in the same ballpark altitude range as the International Space Station. The lowest point of orbit, or the perigee, is going to be around 100 nautical miles on the first orbit, and then it'll get up to about 500 nautical miles in terms of apogee. An hour and a half into the mission, an hour and 20 minutes into the mission, we'll do our stage 2 burn 2 to set up that entry interface. It's a radial burn, and it physically changes the shape of the orbit from a circular orbit to an oblong shaped orbit. Sets up that apogee again at 3,600 statute miles, and our perigee is actually minus 20 miles. And Orion will set up for a guided entry at entry interface at 400,000 feet. In terms of the mission profile itself, Mark Geyer talked about all the capabilities we intend to test. I'll walk through a video here and show you the mission from liftoff to splashdown. On day of launch, we'll be again launching out of Launch Complex 37. At 6 hours prior to liftoff, the launch vehicle will be powered and fueled. The mobile service tower will be rolled back. Orion will be activated. And then at 6:05 Central Time, we'll lift off from Cape Canaveral. The Delta IV Heavy and its 3 liquid boosters will take us out of the Earth's atmosphere. And roughly 3.5 minutes into the mission, the liquid boosters will separate. The core will shut down. The liquid core will shut down about 4 minutes into the mission, and then the upper stage will ignite. After the upper stage ignition, the service module fairings will separate, and the launch abort system will be jettisoned, and Orion will continue its climb to orbit. We'll achieve orbital insertion about 17 minutes into the mission, and we'll begin our first lap around the Earth. At an hour and 55 minutes into the mission, we'll do our stage 2 burn 2, and that'll set up that high Earth orbit as well as our entry interface. During that time frame, we'll be in a barbecue roll, which is rotating about the long axis, and we'll pass up through the Van Allen radiation belts, a period where we expect to see elevated radiation, and we may see some effects on some of our electronics that Mark Geyer briefed earlier. At apogee, we'll see the Earth from 3,600 miles up out the hatch window. It'll be about the size of a 6-foot disc held at arm's length at that point. And then we'll come back around and separate Orion from the service module in the upper stage. We'll activate the attitude control system, orient the heat shield forward, and then Orion will begin its trial by fire. During the reentry, the plasma outside the heat shield could see temperatures up to 4,000 degrees Fahrenheit. After the peak heating period, the heat shield is no longer required. So at that point, we'll jettison the forward bake cover, which is a heat shield that covers up the parachute system, and then begin the parachute's deploy sequence. At that point, Orion will start to drift down on some pilot chutes, and then 3 main parachutes will be deployed. They will slowly unfurl to provide a measured deceleration on the vehicle, and then they'll finally achieve their full open state, leading up to splashdown in the Pacific Ocean off the coast of the Baja. After we splash down, We'll keep the spacecraft powered up to gather some data using the flight instrumentation. We expect some amount of heat from the reentry to soak back into the structure, and we want to understand and characterize the cabin environment before we put our astronauts in there to understand just how hot it's going to be in the cabin. The crew module uprighting system will inflate and, if necessary, upright the crew module leading up to the recovery operation. After we power down the spacecraft, I'll call Jeremy Graber on the recovery ship and let him know the health and status of the spacecraft. And then once we've verified that the health and status is safe on the spacecraft, the recovery forces will come in and recover it. Some small boats will be deployed, and then they'll begin a towing operation into the well deck of the recovery ship. This mission is significant in that it enables human spaceflight to deep space and to destinations that we have yet to have imagined. The aerospace industry as a whole is a tough business, as was said earlier by Bill Hill. Anybody that's been in this business for any amount of time understands that it takes a great deal of fortitude and perseverance. And we intend to test ourselves on this mission, and we intend to test our spacecraft before we put humans on board. With that, I will turn it over to Jeremy Graber, the NASA Recovery Director, and he will brief the recovery operations.
Okay, thanks, Mike. Appreciate the lead in there. We've got a video that I'm ready to show you guys to walk you through a lot of the preparations that we've put in place. As Mike's already described, after Orion's on-orbit operations, spacecraft will splash down in the Pacific about 600 miles southwest of San Diego, and our EFT-1 recovery team will be on station, ready to go to work. The Ground Systems Development and Operations Program here at Kennedy Space Center is partnered with Lockheed Martin, the Department of Defense, the U.S. Navy, to perform several underway recovery tests. These tests were essential to establish and practice the techniques that we'll use to recover Orion, the parachutes, and the forward bay cover from the water. So prior to leaving Naval Base San Diego, the recovery team, along with the Naval Base supporting organizations, will load the recovery hardware onto the U.S. Navy's amphibious ship, the USS Anchorage. Once all of our preparations are complete, the recovery team will embark aboard the Anchorage and head out to the planned EFT-1 landing area. And you'll see a lot of that footage here. In the days leading up to the EFT-1 launch, the team will be preparing the recovery hardware, launching weather balloons from the deck of the ship, monitoring sea conditions, and providing this data back to the mission team as we characterize the conditions we expect on recovery day. Once Orion is successfully launched, the team will perform final preps and launch 2 Navy helicopters that will capture imagery of Orion's descent and splashdown. In addition, those helicopters will guide the recovery forces to the Orion and the other hardware. We'll use rigid hull inflatable boats to secure that hardware with floats until we can recover it. Once Orion splashes down, the crew module uprighting system will get us into this configuration that you're seeing now. If there were any issues, we have an alternate manual uprighting operation that would use inflation bags, as shown in the footage you see here from the Neutral Buoyancy Lab in Houston. Once the mission team has powered down the spacecraft and handover from mission ops to recovery ops has occurred, we'll send in the U.S. Navy divers and Zodiac boats, and they'll check for any hazards. They'll attach a sea anchor to the crew module and a load distributing horse collar and tending lines to allow us to bring the crew module into the ship's well deck. The ship will be set down on rubber supports in the well deck, and it'll be secured in place and finally transferred and secured into the transportation cradle as we bring it back to Naval Base San Diego. In addition, we've got an alternate method for recovery in case there's a reason why we can't use the Anchorage well deck. At sea, we'll install a sling around Orion, and the stationary crane on the USNS Salvor will be used to lift the spacecraft onto the deck, and it'll be secured into the recovery cradle. It'll remain there for its trip back to Naval Base San Diego. We also have the option to tow the Orion spacecraft if there are reasons why we can't recover it onto the well deck or to the deck of the Salvor. And our team is going to be ready. Once we splash down out in the Pacific Ocean, our team will be ready one of the things I want to expand a little bit on is we are going to be very deliberate about our recovery operations. Very good thing about Orion is that it will float. So with this being a test mission, we want to make sure that all of our recovery forces are safe and that we take our time and we're patient about our recovery operations. There are hazards that will remain on the vehicle, and Mike Serafin elaborated on the fact that he will be in communication with me on the ship. Any hazards that the flight team understands and can communicate to us, we'll pass on to the Navy divers who are going to be working the close proximity operations. We want to make sure that they're safe. If we have situations where we need to keep them away, we'll do that. The spacecraft will float. We'll find the right time to go execute our recovery operations and safely bring the Orion spacecraft either onto the Anchorage well deck or onto the Salvors aft deck. And our team has practiced these capabilities, and we're very confident that we're in the best position we possibly can be to recover Orion successfully and safely. And with that, I think I'll pass it over.
Okay, thanks, Jeremy. I'm Ron Fortson, the Director of Mission Management for United Launch Alliance, and on behalf of the 3,600 employees and mission partners, we're really honored to be here at this point, just a month away from the Orion launch aboard the Delta IV Heavy launch vehicle. And we started about 3 years ago on this effort, working with Lockheed Martin to integrate their payload onto our launch vehicle. And over 2 years ago, we actually started the production of the hardware in Decatur, Alabama, to get the booster ready to come out here in order to support all the operations that are going to be going on for the remainder of the count here. So this is the 28th Delta IV launch that we're going to have, and the 8th of the Delta IV Heavy configuration. That Delta IV Heavy configuration consists of a center common booster core along with 2 strap-on common booster cores. And each one of those common booster cores has an RS-68 liquid oxygen, liquid hydrogen engine that provides about 663,000 pounds of thrust each. In addition, there's an upper stage on the vehicle that is an RL-10B, and it's also provided. It, in a combination with the booster engines, are both produced by Aerojet Rocketdyne for us. So at this time, I wanted to show a video that shows some of the processing activities. You can see here, this is 2 of the common booster cores in the second stage on the Mariner. The Mariner is, ships the hardware from Decatur, Alabama. It comes in the wharf just south of here on the base. We then transport it over into our horizontal integration facility there. You can see where we do all the processing of that hardware. You can see in this image here shows the actual common booster cores being mated together, along with the second stage is being mated on top there. There's a launch mount unit there as it gets transported out to the pad. Once it gets out to the pad, we attach it to a fixed pad erector, which is underneath the rocket, and you can see there that essentially lifts the rocket up into position. That all was accomplished on the 1st of October to get it in that facility, and so since then we've been doing a lot of processing activity to get ready. We just successfully completed our wet dress rehearsal yesterday, where we basically took the vehicle through pretty much a launch countdown. We fully tanked it, operated all of our systems, and it was a good exercise, and everything is working great. So we're really in good shape moving forward. Have a few more activities to go. As was mentioned, we're going to be moving the Orion payload out on the 11th, and we're going to stack it on top of the rocket. We'll do some final integration testing along with some final closeouts of the launch vehicle, and then we'll be ready to go on December 4th. So we're really excited to be a partner in this Orion crew-rated spacecraft activity, and ULA has been maintaining our relentless focus on mission success. We know it's critical to deliver this payload on orbit successfully, and that's our primary job during this mission. So thanks again to all of you and our mission partners here for giving us this opportunity to be a part of this mission. I'll turn it back over to Rachel.
Okay, thanks, Ron. We'll go ahead and take some questions here in the room first and then on the phone. As a reminder, if you're joining us on social media, you can send us your questions using the hashtag AskNASA. And if you would be kind enough to please state your name, affiliation, and to whom you're addressing your question. And we'll start with Marcia Dunn.
Marcia Dunn, Associated Press. 2 real quick questions and a longer one. I'm wondering, is there a cost associated with the mission from beginning to end? What is the main hazard that the recovery crew needs to be so careful with? And my third question for Mr. Geyer is there's so much writing on this flight. I'm just wondering how the events of last week have maybe really, how that has added to the stress or tension level of all the people working on this mission.
The cost we put together for this flight is about $370 million. That includes the rocket and includes the part of the vehicle that we're gonna throw away, like the service module panels and the LAS. We're going to reuse the capsule, so the capsule is part of our DDT&E, part of our design work, and we're actually going to fly it again. So that 370 is the rocket and the stuff we throw away and the operations personnel. So I'll let Jeremy answer the recovery, and then I'll talk about the other.
Okay. As far as recovery goes, the environment in the open ocean is a hazardous environment in and of itself. So any of the additional hazards that potentially, nominally, the vehicle coming down should not pose any threats to the recovery forces. But again, it's a test flight, so there's systems that we're not 100% sure we know what condition they'll be in once we're splashed down. We have high confidence that they'll be in great shape, but we've prepared ourselves in case there are some issues. There's propellants on board, there's ammonia on board, so those types of things. We're also radiating for telemetry. So all those things are things we're very familiar with. They're common elements on all spacecraft. We're confident in our ability to manage those, and it's just making sure that if there are issues, we know what they are and we can pass those to the folks that are in close proximity to the vehicle.
I think it's important to mention, too, that this particular flight, we're going to land in a region where we expect the sea state to be worse than where we're nominally going to land. Nominally, we'll land off the coast of San Diego. Now, because of this particular flight, we're going to land off the coast of Baja. December turns out to be a bad time in that region. So the wave heights are going to be higher than we would like for this kind of thing. There's going to be periods where that's the case. So what Jeremy's saying, we're going to look at that on the day of launch, and we may decide, well, the wave heights are higher than we want to send those guys on the boats in there. Things going to float anyway. It's not going anywhere. So we're going to take our time and do that right. So I just want to be clear on that. We believe that nominally we're going to have a safe operation. And the beauty about the well deck, which we're trying to make sure works well, is that we can pull the capsule in the well deck and the crew doesn't have to get out in the water. That's the beauty of this. But it turns out that getting it in the first place, if the seas are high, is a challenge, and that's what Jeremy's talking about. But the advantage of EFT-1, though, if we weren't flying EFT-1, we would have found this late, right? It was a beautiful idea until you actually go out there and start to string it up and try to figure it out. So we're going to take our time and do it right, because this is the one part of EFT-1 where we actually have people as part of the operation. So we're going to be careful. We got plenty of time. So I just want to clarify that. I would say all the folks that are involved in Orion, both the NASA folks and Lockheed people, ground ops, recognize already. We already recognize that space is hard. It takes a lot of energy to put people in space, and I mean force, to overcome the gravity well. We knew that already. We know we have challenges with that, but the whole idea of EFT-1 is to test those things, to learn about where the challenges are so we can minimize the risk when we actually put people on board. So I would say it just reminds us of the risks that we already understood. But we have not changed any of our plans. We did our flight test readiness review a couple of weeks ago. It was very thorough. Would have been thorough regardless of what happened a couple of weeks ago. And we have open work that we're closing as we always do, with our eyes wide open and making sure that we all understand the risks. So that's the way I would say it.
Bill Harwood, CBS News. For Mark or Bill, I guess, I'm a little fuzzy on roles and responsibilities in terms of who has the ultimate go, no-go, the different points in account where which team has the responsibility for saying proceed or don't proceed, just given the commercial nature of the contract. So I'm confused about that. And just to follow Marcia's question, if 370 is everything but the Orion capsule that you're going to reuse, is there anything we can get some sense of what's been spent on that piece of hardware up to this point, realizing you're going to use it again?
Yeah, so I'll address that capsule itself is part of what we call design, development, test, and engineering. It's part of getting a design ready to fly people. So it is a fraction of the total to get to the first human flight. That full scope of cost is what we're working through this next few months, you might have heard something called a key decision point memo. SLS just put one out. You might remember that. We're in the process of formulating ours and getting that total number out to what it costs to full flight. So I don't break out the specific capsule as a part of that. But we will when we have that full cost EM2 and what it takes to get to the human flight, we'll broadcast that and we can talk about it then. A great question on roles. Bill said it very well. We've contracted this particular launch as a service. So we said, Lockheed, take the capsule that we built under DDT&E and the other systems and fly it, and I want this data. Here's the objectives I want to see. I want to see heat shield performance, blah, 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 all these kind of things. So we give them a list. So they went out, contracted the rocket. They do the rocket integration. We're not in the middle of that. And they are in charge of the whole mission. So Brian, here's the mission manager from Lockheed. Again, in a sense, he subcontracted out MOD and subcontracted out ground ops to do those particular parts, but Lockheed's responsible for the integration. As far as the go, no-go calls, it's very clear. At the beginning, and launch countdown, it's all ULA, right? They're in charge of the whole counting down, making sure the rocket's ready to go. We, as a payload, will give them inputs as to whether there's an issue on our side, just like there would be any other ELV launch. So it's very consistent. Once we're in orbit, Mike Seraphin and his operations team is in charge, and they have a set of flight rules and procedures that we have all agreed to and signed off, just like it would be on a shuttle flight. Mike's in charge. If something goes outside those flight rules, it comes back to a mission management team, just like we do on the shuttle. And as Brian said, that mission management team is in Hangar AE. Brian's in charge, but NASA's also part of it. I'm there. We have safety and engineering. So we'll talk about the particular issue, and we'll caucus and make a decision. But then Mike will make the call and forward that on to Seraphin, who's mission operations. So that's how it runs. Did I? Yep, good.
That's fine.
It's a great question.
And a final quick one from me. What kind of rocket cam stuff can we expect during this flight? You mentioned seeing the Earth out the window, but what kind of cameras are on board, and what can we expect to see in real time?
We'll have we're still working on exactly the bandwidth and when we can show these, but we'll have rockets on the we'll have rockets on the cameras. We'll have cameras on the rockets, so it'll be looking up. We expect to see separation events, the fairings and the last. We'll have cameras out the windows too. So there should be some selected views as we're flying, and certainly as the parachutes come out, that kind of thing.
Stephen Clark with Spaceflight Now. A couple of questions. First of all, can you walk through what's lacking on this spacecraft, what you need to introduce for the EM1 mission to support crew inside the spacecraft or outside the spacecraft, I guess, and for Ron Fortson, can you talk about the modifications, if any, to the launch vehicle and also to the launch pad to support this very unique payload? Thanks.
Yeah, so I'll start with the crew module, which is the key. So we're flying the structure, we're flying the heat shield, we're flying the parachutes. The computers are the same that will fly people. We'll fly with people. We're going to add a third string. So basically, I have two sets of computers. I'll fly a third when we actually put people in. So we add redundancy is one way to think about it. We'll also add the seats, and we'll add the displays and controls, because you don't need those. There's nobody to push the buttons, right? You don't need the displays, and the software to support that. So that stuff we'll have to add. On the service module, that's the big add that we'll do on EM1, where ESA's providing the back end with the radiators, the prop system, the solar arrays, and we'll provide that avionics ring, which has a lot of the interfaces that help run the service module. So that's the big piece that's different between this flight and EM1 is the service module. And then when we actually go fly people, we'll put an active abort motor and an active attitude control motor on the last, because we'll want to make sure that as we're flying, if there's an issue with the rocket, we can get people off safely. So those are the big changes.
So as far as the launch vehicle is concerned, the booster itself is pretty much the standard Delta IV heavy configuration. So there's been no significant modifications to the booster itself. Now, as far as infrastructure, there were some changes that we had to make to accommodate the EFT-1 configuration with our swing arm. So we essentially had to remove our swing arm, which has a lot of the umbilicals connected to it that interface with the payload. We had to take that off and actually do some modifications to that swing arm so it could support the unique requirements of this mission. So we did that in August. We did all the repairs, did all the modifications we needed to, and put the swing arm back on. and it did that all in August and did all the qualification testing on it. There was also some umbilical works we had to work, make some changes to accommodate the uniqueness of this mission, but primarily that was the major changes we had to do to support this mission.
Okay.
Jay Barbary with NBC News. There's been a lot talked about what the early missions will be, assuming this goes well. Could you address that? I understand we're going to do a figure eight around the moon, but the first real mission will be to dock with an asteroid placed at Lagrangian point number 2, which is about 38,000 miles, I think, beyond the moon. I'd like to know length of those missions. What are your keeping you now from radiation? How are you going to handle radiation? I understand a 9-day mission out there. And what will be the basic configuration of Orion as service module? I understand there's a habitat that with a laboratory on board, but you still have these things in flux, and you're working on them. So can you give us a little idea of what the early missions will be like, and when will they be happening?
Yeah, for EM1, we're actually going to go into a distant retrograde orbit, very similar to what we use for the asteroid retrieval mission. It's different than L2 in that it's goes around the moon, but it's in cislunar space. So we're going to do that for EM1. EM2, when we add crew, we haven't quite decided yet which way we're going. We would like to repeat that mission to enable our operations in cislunar space and to test out some things. We may test out a extra vehicle activity or a spacewalk in preparation for the asteroid retrieval mission, and then we'll do a series of missions, one of which is the asteroid retrieval mission that will sequentially start buying down risk of what we need to do to go to Mars. As you mentioned, at some point we're going to probably need a habitation module. Orion is somewhat constrained in that it's good for 4 crew for 21 days. So we'll have to augment that as we get the longer missions. But we're in the process of formulating those, and sometime after the first of the year we'll be talking in greater detail on those.
Okay, let's do one more here in the room, and then we'll go to a question on the phone. Go ahead.
Can you give us any idea on a timeline right now, what you're thinking?
We are taking a look at, after EM2, trying to do a mission every year. We'll see if the budget supports that. We believe it does right now. Obviously, we're going to have to figure out a way to reduce costs for operations, and we're addressing those now. And then we'll have to build, kind of a funding wedge to develop other things like a habitation module or other things. We're also looking at, can we partner with some of our international partners, similar to what we're doing with the service module with the European Space Agency? Can we get other partners to bring on other capabilities that we know we're going to need to go into deeper space? Thank you so much. Sure.
Go ahead.
Daryl Nail with Orlando Fox. You mentioned that the heat shield is a critical component that you're testing in this. Can you compare it to the technology? How similar is it to that used during the Apollo program? And how different is it? What changes were made to it?
Yeah, great question. So first of all, the materials are different. Even though it's similar, there were some materials in the original 1960s version that were carcinogenic. So we had to change some of the materials that are in the makeup. That actually changes the performance a bit, and so we had to do testing and certify that material. The other big difference is the size. So Apollo's about 3.7 meters. We're 5 meters. That changes part of our entry. It also changes the aerodynamics and changes the material, the strength properties of the heat shield. So that's the big difference. So we used what made sense. We used the stuff that applied, and then we had to change some things.
Okay, let's go to a question on the phone with Miriam Kramer from Space.com.
Hi, thanks so much for taking my question. I am just curious, when are you potentially expecting to refly the capsule, and what kind of flight might that be? And also, what kind of wiggle room is there with the launch date? Can you fly on December 6th if need be, or December 4th, or how many days can you basically split before you kind of have to stand down? And thanks.
Yeah, good. I'll let Brian address the launch date stuff. I'll tell you that for us, let's see. Our plan is to get the capsule back. We'll clean it up. It'll be used for what we call Ascent Abort 2. That's our acronym for our next launch abort test. You saw a nice picture of the launch abort system on top of the Orion. One of the most stressing cases in an abort case is when the rocket is going through the max dynamic pressure or transitioning to Mach 1. It's a very difficult region to be able to predict that we can actually control that launch abort system as we're flying. If it starts to tumble, it'll break up. So we have done a lot of wind tunnel tests, but we believe there's still enough uncertainty we need to fly it. So we'll take that capsule, we'll put a launch abort system on top of it, we'll put a Peacekeeper stage, which we get from the DoD basically for free, and we fire it, and it puts us in the right conditions, and then we activate the LAS and make sure that we can fly it. So it's a great test for us, and it's a great way to reuse this capsule, and it'll give us a lot of great data about how the abort system functions.
As far as our launch dates and our opportunities, we're scheduled on the range for 3 days right now, December 4th, 5th, and 6th. Of course, the 4th is our primary day. If we have to fall off of those days for either a weather problem or either launch vehicle or spacecraft anomaly that we need to work, those will just be like those of you who are probably used to other shuttle flights. We'll take those day by day depending on what the severity of the problem is. If it's the weather, we'll try again the next day. In general, we've got the 3 days with the rest guidelines that we invoke both with ULA and with our team as well too. And we've got a healthy launch window of 2 hours, 39 minutes. It's possible we could try those first 2 days and then need to stand down on the third, or depending on the weather, and folks around here have seen how we do this sometimes. We'll try the first day, and depending on what the weather looks like the next day, invest our time to rest up and then try again on the 6th. If we move past those days, then it just becomes a negotiation and discussion with the range. There's, I believe, SpaceX and another launch comes up after that several days later. So it just depends on how the vehicle's postured and what its availability is. But generally, once we're on the range and it's a day-by-day type of delay, we'll generally slide and still maintain a launch posture throughout that time. And of course, we're coming up against the back end with Christmas and the other holiday times that might have us stand down. And we got another element to that in their scheduling, and that's the recovery ship that's sitting out there. Folks getting a nice tan, I guess, while they're waiting. But ultimately, we've got to take that into consideration, how long our delay is and whether that ship has to come back or the people need to get some servicing done on their provisioning as well, too. So there's a number of facets, but generally it's going to be day by day. We've got 3 days on the range we're hoping to get off in those 3 days.
Okay, we'll take another question on the phone, and then we'll take some from social media. On the phone, we have Jason Davis with the Planetarium Society.
Hi, it's the Planetary Society. It sounds like you guys are really interested in getting images of Orion when it's under parachute coming back, and I assume that's for heat shield performance. So I just wanted to get a feel for how important it is to image the heat shield before it hits the water, and then how you'll characterize how well the heat shield performed. Is this just a visual observation to see how well it did, or will the sensor data also help you with that? Thanks.
Yeah, there's a great question because there's a lot of things we're trying to do relative to the heat shield. First of all, though, it is one of the key things we're going to use with the helicopters that are on site are going to be filming the parachutes, forward bay cover, and those kind of things. So that is also a key objective for us, see how it behaves under the parachutes. We are going to have imaging, though, with some assets. There's a P3 that we're using that will actually thermal image the heat shield, give us some data, temperature data. We'll also, once it lands, we're going to take a lot of pictures of it, and the recovery guys know that that's one of our main objectives. So Jeremy's guys are going to be very careful as best we can with the heat shield so that we don't damage it on recovery, or because we're going to actually measure the erosion and where it eroded, and so then correlate that with our models. So that's a big deal. As you said, obviously we have a bunch of sensors on board. We get a lot of measurements of temperatures, and we actually have a radiometer that'll measure through actually a piece of ruby. We'll be measuring the plasma out in space behind the heat shield, which is a key piece of data we haven't gotten before. So there's a lot of ways we'll be looking at the heat shield.
And Mark, I can
Yeah.
talk a little bit more about what we'll do from a recovery perspective. Once the Navy divers are given the go to approach the spacecraft, and they establish that it's safe, one of the first things they'll do is we'll do a subsurface dive to take high definition video and still imagery of the heat shield. And we'll verify that we've got very good imagery before we really start getting into the recovery operations. Prior to approaching, we will also be taking thermal imagery from a small boat from a distance. That's when the vehicle is still powered up and has essentially initially splashed down, and we'll be capturing thermal imagery from that aspect as well. So, and then we will be taking pictures and video of the spacecraft, focusing on the heat shield all the way through the entire recovery process. Once we've got it secured down in the well deck, once we rinse the vehicle, we'll take additional imagery, and we'll focus in on the very specific areas that wherever there are erosion events or any other items that are identified by the experts, we'll get very high definition imagery of each one of those.
Okay, let's take a couple quick ones from social media, and then we'll go ahead and conclude.
All right. So we're getting from social media, ask NASA, is Orion designed for sufficient radiation shielding for a round trip to Mars?
So the Orion would be, you would use Orion at the beginning of the mission and toward the end, right? So as Bill said, it's really designed for those parts of the mission and to handle about 20 days in space. So to go to Mars, you'll need the other elements, the HAB module where we can have more exercise, the food and everything else, and the big propellant systems that'll actually push you there. So for those missions, those are the systems that will be working the radiation part. Our part just really needs to protect the crew at the beginning and at the end. But we know for 21-day missions, it's really not a crew issue. And for those missions we're going to do in cislunar space, the radiation is really a big driver for the computers. If we do have a solar flare issue, there is a way, we have a design where we can actually take the stowage items and give the crew like a safe haven area like they do on space stations. So that's our plan for when we're in Orion.
Okay, so kind of along those lines, will EFT-1 Orion be gathering data on what the crew would experience in flights such as G-loads?
Yeah, that's a huge part of it. So one, we do have radiation sensors on board, for example, so we'll actually measure in different parts of the vehicle what we're seeing, what the actual environment is inside. And then I mentioned the heat shield instrumentation, but we have 1,200 sensors. A lot of those are loads, so they measure the impact loads when we land, ascent. We'll get acoustic data inside and out, so we know how loud it is, those kind of things. So a lot of that is for the vehicle, but it's also about to understand what the environment for the crew is going to be.
Okay, so the next question is, what happens to the upper stage after Orion separation? Does it just burn up and re-entry?
I'm trying to recall if it actually comes back in.
It'll come in.
It is going to come back in
It'll do
eventually,
its
yes.
final disposal burn after we separate. Orion separates from the upper stage and the service module. We'll each go about our separate ways. We'll go in through our entry trajectory while they also have their deorbit and disposal burn that we'll schedule and bring them back, largely breaking up as it enters Earth.
One that kind of goes back to the Apollo questions is, in terms of internal size, how does this compare to the Apollo capsule?
So the key part, I think, is the diameter is significantly bigger, and on the inside it's like a very large cubicle. So if you've seen the pictures, it's built really for 4 people, where Apollo was built for 3. But we're also big enough that we could handle 6 for short duration, so it gives you a sense for the size. So to me, it gives you more flexibility. Wherever these destinations are, whether we're doing the asteroid or we're doing other missions, by carrying 4 people, think about it, you can do 2 EVAs, switching off EVAs, where before we really counting on 1 and then waiting. So it gives NASA a lot more flexibility in how we explore, is the way I would look at it. And I did want to clarify a little bit about the heat shield. One of the other big differences in Apollo is if you look at the sides of Orion, if you look at Apollo, it was AVCOAT all the way around, bottom and sides, which were very heavy. But on Apollo, or on Orion, we've used the experience we gained from shuttles. So the back shells are actually very, very much like shuttle tiles. They're lighter, and yet they're able to provide the heat protection that we need for our missions. So we advance the state of the art where it makes sense and adapt to that. So that's one of the big differences between us and Apollo, too.
Okay, with that, I'd like to thank everyone for joining us today. You can learn more about Orion and track all the events planned leading up to the flight test at www.nasa.gov/Orion.